Bienvenidos de nuevo a CyberCamp 2015. Os vamos animando a que os acerquéis al auditorio. Es prontito, pero nosotros ya arrancamos este último día de este gran evento.
We're going to start the third and last day of this marvelous event. We're about to finish. So many activities, workshops still to be conducted. The very first paper, Marko Maric, he is computing engineer and he got a master in sciences of information and telecommunications. During this last year of studies, he focused on cybersecurity. He's working on tools as to detecting and responding to incidents. And over the past years, he's been part of the Advanced European Cybersecurity Center. It's really a pleasure to have you here.
Basically, I don't speak Spanish. I don't know to say anything but "Hola, ¿cómo estás?" So I will need to hold this presentation in English. So yes, how come that I am into Bitcoins? Well, basically, as a member of Croatian National CERT, we had a lot of situations of blackmailing. For example, recently we had one hackers group in Croatia that was doing a DDoS attack on some firms in Croatia, and they were asking for ransom in Bitcoins. And as well, we often know that there are many ransomwares around the world, and ransoms are always in Bitcoins. And of course, as my job is to catch criminals, I started to wonder myself, would it be possible to de-anonymize the Bitcoin addresses that those criminals are giving to the firms, that the addresses at which they want their payments to be made. And yes, basically I started to research what are my chances to de-anonymize some Bitcoin address. So I suppose everybody here who was interested in this presentation knows something about Bitcoin, but for those of you who does not know anything, I made just a brief introduction, just for the sake to introduce main elements that one needs to understand to be able to understand the anonymization methods. Basically, there are two complementary anonymization methods. One is transaction graph analysis, and another one is real-time network analysis. And I will say something about how each of it works, what are the chances to de-anonymize anything, and can I have some realistic expectations of those methods. Okay, so let's start with introduction. So what is Bitcoin? Bitcoin is a peer-to-peer network where users are transacting digital money between each other, and the peers that are actually users are generating transactions and broadcasting them on network, and they are broadcasting those transactions to each peer that is neighbor of the peer in question, and then subsequent peers are transacting further. So in the matter of few seconds, the whole network is aware of some transaction that took place. Something wrong. So on the other side, there is a subset of those peers called miners that are collecting those transactions and putting them on the pile. And together with those transactions, they are adding some random data that in such way that the hash of those collected transactions plus data is generating hash which meets some specific condition. That hash is not easy to find, and miners need to be fast and need to be lucky to be the first one who will generate the block. Miner that first generates the block is broadcasting that block to the network in same manner that our transactions are broadcasting. And so basically block is containing transactions, and all peers are learning blocks individually, every peer for itself. But at the end there is consensus, which I will not talk about. It is outside of this talk. There is consensus that puts state that every peer actually has a same sequence of blocks on their computers, and that sequence of blocks is called blockchain. The blockchain is basically a set of all transactions that ever took place in the Bitcoin network. Okay, so now I start with the first method of de-anonymization, and that is transaction graph analysis. So here I need to say something more about transaction itself. So in the picture you can see that transactions are split on two parts, that is input part and output part. On the input part are all Bitcoin addresses that are sending the Bitcoins, and the output part are all Bitcoin addresses that are receiving the Bitcoins. So why is transaction graph analysis possible? Because the blockchain is public, so everybody can see him, but though he is the public, identity of those Bitcoin addresses is hidden. So Bitcoin address is basically just hash of the public key of the user, that is owner of that key pair. And as picture suggests, there is three main concepts that you need to be aware of to be able to speak about the anonymization. So the first concept is that input is always equals output. So if you have 10 Bitcoins and you want to pay to somebody something worth of 7 Bitcoins, you actually need to spend all 10, but 3 Bitcoins that are left over, you need to pay to yourself back. So therefore, as if you look the second transaction, you have always one additional Bitcoin address that is actually change address, and that is the address when you paying the coins back to yourself. Except that there is also a transaction fee, as you can see on picture, and transaction fee is the reward for the miner for his effort to secure the network. And if transaction fee is the transaction fee bigger, the miner is taking your transaction as privileged transaction to be included in block, what is complementary. If you don't pay the transaction fee, then you may wait quite a bit to get confirmation that you really paid something. How to de-anonymize using blockchain? So how is possible to de-anonymize something if you have only Bitcoin addresses that looks like random data? So basically there are two concepts that allows the de-anonymization. First concept is wallets. So basically every user is owner, or is very often owner of multiple Bitcoin addresses, and when he's doing big payment to somebody, big payment, and he have no enough coins on one address, he need to use, on input side, he need to use many addresses in order to execute transaction. So basically, when we see in blockchain some transactions that have multiple Bitcoin addresses on input side, that means that all of those addresses are owned by same user. So that is not the anonymized user, but it is something to know that they are all owned by same user, by same entity. So in that way, the wallets are actually proof of share control. So if you see that some transaction is assembled from multiple Bitcoin addresses, they all belong to same user. Second thing that enables the anonymization using blockchain is the fact that many people are publishing their Bitcoin addresses publicly on the web. So, for example, on many forums you can find people making signature using their address, and on blockchain.info, which is main blockchain explorer, there's an option to tag itself. So you can, if you are running some service or some website, you can some service where you are somebody needs to pay you something, you can add your Bitcoin address to the tags, so people can use this registry to find you. So basically, what we can do is by crawling the web, by crawling the forums, by crawling the blockchain.info. They do not have some specific AP, so it is need to be done by crawling. We can collect all tagged addresses. Other way of collecting tags is by to say active pinging. So, for example, if there are some merchants places on the web and you want to know which Bitcoin addresses they are using for payout, you can on purpose buy things just to generate transactions to collect all those addresses. Okay, so now when we are aware of concept of wallet and on concept of tagged users, we can use method of clustering to actually produce even more tagged addresses. So there are three main things about clustering, three main methods that are to be used. First of it is linking different inputs to same user. So if you have two transactions, one with inputs A and B, another one with inputs B and C, it is obvious that and E and B and C are belonging to same user. So in this way, if you have users with a lot of Bitcoin addresses, on time by time you can achieve very quick expansion of that cluster. Another thing is tagging clusters. So when you have when you were doing the first step of linking different inputs to same user, you achieved a very big cluster. And if you are able to find any of address from that cluster to be associated to any of tags, you can immediately tag all cluster to belong to same user. And finally, when you have clusters, different clusters that are tagged with same user, you can combine all these clusters to one single user. Exactly such approach was done by the researchers of University of California in December of 2013. So it was just in the time of Bitcoin boom when price rise exponentially as well as hashing power. They parsed blockchain, and basically even now there is on the GitHub few different available projects that are doing softwares for efficient parsing of blockchain. And in the analysis of December of 2013, they managed to extract 16 million transactions and 12 million public keys, that is 12 millions of Bitcoin addresses. And when they did clustering based on the method I said on previous slide, they managed to produce 5.5 millions of clusters. And when they combined clusters using the third method, they end up with 2,000 clusters less, which is not something, but there was, for example, a lot of clusters that were tagged to then main cryptocurrency exchange MTGOX, and they excluded so-called sync addresses from this clustering. Sync addresses are addresses that own some bitcoins, and those bitcoins haven't been spent since 2011, so 2 years after Bitcoin was invented. So those addresses are belonging to users that was a part of Bitcoin experiment, and actually they probably thought that it will never worth anything, so they just lost their wallets. And at that point, in December 2013, 64% of all Bitcoins were actually in sync addresses, so unable to use. So in circulation was only like 36%, and now is in circulation about 60%. Okay, so there are some privacy recommendations, taking into account that everybody is aware that the anonymization is possible. So use new addresses to receive payments. This recommendation is there to enable somebody to see what types of transacting you are doing. Other one is to use multiple wallets for different purposes. So if somebody enforces this privacy recommendation, in that case, I'm unable to expand the cluster quickly. And the third one, which is the most important one, Bitcoin address should be only used once. That means that whenever you are paying something and you have leftover, that leftover you should pay to newly generated address and not to already existing one. Why is that important? So if you have change and you return change to your own address, then it is obvious from the picture. Then it is obvious that A paid B, and if you in the case if you paid something to two party, then it is obvious that you paid to B and C. But if you use the newly generated address, so in the second row, first picture, then it is not obvious if you paid to Bitcoin address B or C. And even further, if you use the same privacy recommendation, and then from your change C you pay to party D, and left over is E, from the perspective of somebody, he doesn't have any clue who is the payer, who is the payee. So that is the most important recommendation. And it is possible to go against her, and the same researchers from University of California managed to actually add change address to the inputs, no matter it is so much hard to recognize. So basically, there is multiple types of change handling methods that wallet software are implementing, and but basically they are all following same policy, that change is always added to newly generated address, and user can turn off that option, which is not good for him, because then it's easy to recognize the change address, obviously. So there is no any exact algorithm how to recognize change address, but there were some efforts. First effort was to use the fact that user rarely issued transactions to two different users, and this is completely obsolete now, because, for example, on gambling sites where you have game that wins multiple people, then they are making payouts to multiple persons, so you can't use that fact. The second fact, change address amount is not greater than lowest input amount. Now, this is to say logical, because if change address amount is greater than lowest input amount, then it means that you could execute that payment without that lowest input amount. But wallet softwares are aware of that, and they are obfuscating that in the way that they are always using the scheme of taking the set of input addresses in such a way that you can't use this approach. And the third one, heuristic approach, is change address is used only in one output over all past transactions. This is actually the best approach, and only one that can be used nowadays. So if the change address is used only once, is used only if change address is used only one output over all past transactions, that means that actually you are tracing this third privacy recommendation. But the question is it safe? Because maybe somebody made payment to someone who still didn't do any transacting at all. So that is the only problem in this approach. So now we're going to see results of change address heuristic that took the third approach. So add to input list all addresses that is used only once in output over all past transactions. And this kind of experiment resulted in 4 million change addresses, and it was 13% of false positives. They managed to recognize false positives based on the fact that when you are looking into blockchain, when you are looking into blockchain in one point in the time, all transactions that are up in the blocks are actually transactions that took place in the future. So you can see if that output address was actually used again. If yes, that means you have false positive. But when they started to take a better look of those false positives, they managed to understand that 12% of those addresses were actually payback addresses. So it was used by the service that is paying back the money on the same address that you use to buy whatever that service is offering. So it turns out that actually it is only 1% of false positives. And if they tried further with some improvements, and they actually try to wait for 1 day so they can see if the address will be used again. And in that way, they reduce false positives to 0.28%. In 1 week, if they wait for 1 week, they reduce to 0.70%. But even with 0.70%, they end up with mega cluster containing all these services. So what happened is that there was a few of addresses that managed to link clusters together, and they were actually not change addresses. So you have complete disaster only because of few addresses. But then they actually took another view on those specific addresses and what happened with them, and they realized that some addresses were used two times as change, which is completely not something what you will not see every day. And so they excluded those cases, and they end up with 3.5 million of change addresses. There was no mega clusters again, and they managed to tag 2,197 clusters, which is 1.8 million addresses. And they started with 1,000 of tagged addresses. So with the approach of collecting addresses from forums, of active pinging, of collecting tags from blockchain info, you are able, they collect 1,000 of tag addresses, and they end up with 1,800 times more. So it's really good result. How this can help me in my work? So basically, I hardly doubt that I will, with this method, directly de-anonymize the adversary, the attacker, the criminal. But what is possible is to find transactions where, for example, cryptocurrency exchange made the direct payment to that criminal, or the criminal did direct payment to exchange. If there is investigation open about this case in Croatia, then I can, with the effort of law enforcement agencies, I can basically catch the attacker in that way. But without investigation, I'm probably not able to do anything. Okay, so that will be it for transaction graph analysis. Now I'm going to tell you something more about real-time network analysis, which is, I think, more interesting. Excuse me. So real-time network analysis is basically a method to linking Bitcoin addresses to IP addresses. So this is something different than linking Bitcoin addresses to some tags find on internet. This method is possible to distinguish different users even if they are behind network address translators. So if you have multiple Bitcoin clients behind NAT, this method is able to label different clients even if they using same public IP address. I will say later why is that possible. And method is able to link different transactions to same user, even if they look completely unrelated in transaction graph analysis. So if I was unable to link some addresses in the transaction graph analysis, real-time network analysis can do it. So basically, real-time network analysis can enhance the transaction graph analysis. Okay. So what is the problem? Problem is, of course, using of proxy, because then you do not de-anonymize the actual IP address of user, but you de-anonymize the IP address of proxy. And actually, there is a solution for that, and that is to simply shut down Bitcoin over Tor functionality. So I know that it sounds amazing, but actually it is possible to do. You can shut down the whole Tor network, and it is quite simple to be used by any users. And I will explain that in a moment. So actually, we need this shutdown, so we can observe the real-time network analysis on ClearNet, like there is no anonymization techniques used. Bitcoin is peer-to-peer network, but actually we could share the peers in two different categories. One is the peers that are clients, and the peers that are servers. I put under the codes because it is not really client-server architecture, but rather the thing is that clients are the peers that are able only to initiate outgoing connections. So those are home users, and servers are peers that are able to receive incoming connections. And each peer, whether server or client, is trying to connect to 8 entry nodes. So Bitcoin have network discovery mechanism that is used for each client to be connected to 8 entry nodes. Entry nodes are, of course, always servers, because clients can't see each other. So basically, Bitcoin does not use any not traversal technique, but clients can reach each other across the servers. And what is important to remark is that servers can take at maximum 117 incoming connections from clients, and everybody is initiating 8 outgoing connections. So in total, there is 125 connections possible for each peer. In this case, only for servers. So how is possible to distinguish the clients behind that? It is possible because this approach of real-time network analysis is actually labeling clients in the way that it associates clients with its entry nodes. So every client in this technique is presented as its entry nodes. Okay. And just information that currently there is 8,000 servers and 100,000 of clients in the network. Okay. So how to disconnect Tor and in that way actually have to say a clear situation of dealing with real-time analysis on ClearNet. Disconnecting Tor is possible by exploiting Bitcoin's DOS protection, building DOS protection. So basically, when one peer is delivering malformed messages to some other peer, that other peer is banning him for 24 hours. So he is cutting connection with him, and he is not allowing him to establish another connection. So now I'm talking from the perspective of attacker. Actually, I will be attacker when I will be doing this de-anonymization. Attacker needs to establish connection. So first to say, in this scenario, I'm observing that there is only 2 exit nodes in Tor network and only 3 Bitcoin servers. So attacker is establishing connection with each server and sending malformed message. And he is doing so going through each of exit nodes. So in this way, you have the situation that all servers banned all IP addresses of exit nodes. And now when we are looking the clients of the client part of Bitcoin network, and if they try to connect to network using Tor, that they will be unable to do it for the next 24 hours because all servers are banned through all possible exit nodes. And I was watching recently at Tor metrics. There is around 1,000 of Tor exit nodes, and times 8,000 Bitcoin servers, you get that you need to upload 1 gigabyte of traffic of malformed messages actually to exclude all Tor network from usage for the Bitcoin. Okay. So first part of real-time network de-anonymization is to learn entry nodes of clients. To do so, I need to explain something about address propagation mechanism that is part of network discovery protocol in the Bitcoin. So what is address propagation? It is basically the mechanism that is making the network alive. So nodes are all the time coming and going, and coming to the network and go away from the network. And basically the peers need to learn all the time which are nodes available. So if their entry nodes if their network nodes leave the network, they are managing to find another entry nodes. ADDR message is a message that every peer sends to each of its connections after the peer connects to the network. So every of his entry node is aware of its address, and those entry nodes are propagating further in the network ADDR messages. So basically, in the matter of few seconds, you have plenty of nodes in the network that are aware of new clients that approach to the network, that made connection to the entry nodes. There is one detail that is very, very important, and that is that addresses are propagated in the way that always is choose 2 responsible nodes. Each node is choosing 2 responsible nodes that will receive the ADDR message and that will forward the ADDR message further in the network. And basically, when one node propagates some ADDR message with IP address included, he will not propagate over that connection ADDR message ever again. So it happens only once. Okay? Okay, I promise I will not go deeper than this. This is technically the deepest thing of the presentation, but I need to say in order to explain the attack. So how to choose responsible nodes. So when some peer receive ADDR message, he calculates hash for each peer he is connected to, and hash is the function of 4 variables, and that is the address X that is inside of ADDR message, some random salt, current day, and the address of peer structure of the peer that is candidate to be chosen as responsible nodes. After that, all hashes are sorted, and first 2 hash are chosen to be the responsible nodes. The peers that are associated with 2 first hash when hashes are sorted. Okay. So now I'm going to explain how to learn entry nodes of some client C. How is attacker able to learn those entry nodes in this very simple configuration where you have only 5 servers and only a dozen of clients. So what attacker needs to do is maintain a very big number of connection with each server in the network. This way, when the client connects to the network, he chooses some entry nodes. For example, in this case, client chooses entry nodes 2, 3, and 4. Now, when client starts to propagate its ADDR message with his IP address for other nodes to know for his existence, it is to expected that node number 2 will choose the attacker as responsible node, that because the fact that he have a lot of connection. Of course, so this way the attacker will receive ADDR message over the entry nodes of client C, and then the attacker knows that client with the address CA has entry nodes 2, 3, 4, sorry. But what is the problem with this approach? Yes, chances are big for attacker to be chosen as the responsible node because very big amount of connection, but also there is a possibility that server choose some other node as responsible, and he sends ADDR message to node 1 in this example. And let's say attacker was lucky with other 2, and he received ADDR message over nodes 3 and 4. So we now have the problematic situation where attacker learned that address of client with the address CA has entry nodes 1, 3, and 4, when that is not true. He have entry nodes 2, 3, and 4. So we have a false entry inside the associated list of that IP address we are trying to de-anonymize. Solution to this problem is based on the fact that same address is never resent over same connection. So the next strategy is proposed. It is proposed for attacker to broadcast ADDR message of the address he wants to de-anonymize, so that the responsible nodes which are not attackers one are excluded. it's hard to understand it by words, so I'm going to show it in picture. So basically, attacker connects to all servers, and he sends a DDR message of client C, and servers are choosing responsible nodes. In this case, servers are having only 1 or 2 connections, and therefore they will choose as responsible connections all the connections on the picture. Now, the attacker disconnects, and he connects again with a very big amount of connections to each server. And now, if server decides to have a responsible node, node 1, he will not be able to send the IDDR message over that connection because he already did so, and he's never doing it twice, as I said before. So what's going to happen is that attacker is going to learn entry nodes of the client, but only the subset of entry nodes. So he learned that client with address CA have a subset of entry nodes 3 and 4. Now, some math. Why is still de-anonymization possible? If we have situation that we are unable to learn all entry nodes of some client, where basically peer can be uniquely identified if we know only 3 entry nodes. And that is because it is very unlikely that you have collision of two different clients having the same 3-tuple subset of entry nodes. So it is very unlikely. So the conclusion is that you need only 3 entry nodes. You need to learn only 3 entry nodes in order to de-anonymize the client. Another thing is that if you are able to maintain 35 connections to each server, in that case, you stand a 50% chance to become the responsible node, and that ADDR message is forwarded toward the attacker. So that means that on average of 8 entry nodes, you will receive 4 ADDR messages. And as I said, the 3 entry nodes are enough. How often to broadcast address? Experiment done on University of Luxembourg showed that 10 minutes seems to be a reasonable choice. So the first part of strategy, when you need to broadcast the IDDR message that you are trying to, that contain the address you are trying to de-anonymize, so resending of that address is needed to be done each 10 minutes. If you do it more rarely than that, if you do it each 20 minutes, you are putting yourself in a situation that server can change the responsible nodes, and then you can again have the false entry inside the set. Okay. So what do we have at this point? At this point, we have example. As example, we have we learned entry nodes of three different clients: CA, CB, and CC. And now is the question, how to de-anonymize transaction. So how to know if some transaction is belonging to node CA, CB, or CC? Well, this de-anonymization is possible thanks to next propositions. Client and attacker are connected with one hop over entry node. So entry node is only one hop, and all other connections between them are 2 hops or more. So it is reasonable to conclude that attacker will see transactions coming from entry node before then from any other. Of course, this is the reasonable to conclude, but for example, network latency on the links between the entry node and the client can be much bigger than over some other parts of network, and in that case, you may receive transaction before from some non-entry node than from entry node of the client you are trying to de-anonymize. So that is the problem. But let's just see what are the odds for such thing to happen. If we observe the situation when client is directly connected to attacker through entry node, then we have a situation that 5 messages needs to be exchanged, 16 checks needs to be done by the entry node before he sends transaction further, because every node is first checking is making the validation of a transaction before checking it further. And we have some random time that needs to pass before the transaction is sent. And if we have 2 hops, then we have 8 messages, 32 checks, and 2 random trickling delays. So basically, it is to expect that we will receive the transaction before from the client's entry node, then from some other node. Okay. And some final things for de-anonymization. How is it possible to be? So, I'm going to demonstrate example where we successfully de-anonymize transaction 1. And just to remember, the entry node sets of clients CA, CB, and CC were as follows. Okay, so we take first 15 transactions because we are expecting that between first 15 transactions should be the entry nodes of the client that sent that transaction. And when we do intersection with entry nodes that we de-anonymized, we get situation that intersection have so big cardinality, so big sets, that it is ambiguous if CA or CB or CC generated transactions. So basically, you can't know who generated because you took too big set of entry nodes. And on the other side, you can take very few of the nodes that first sent the transaction, and then you have situation that intersection is very small. In this case, cardinality of each set is 2, so there is no enough cardinality to distinguish client. And I remember you that I said it is needed 3 entry nodes. It is needed 3 entry nodes to distinguish some client. The same research from University of Luxembourg showed that best balance is actually first 10 nodes. So if we take first 10 nodes from the ordered list, of the transactions we received, we have situation that only address CA have cardinality of 3, so node CA generated the transaction. In this way, we actually managed to associate IP address with the transaction. Okay, so basically what the guys from the Luxembourg did, they set up a testnet with 250 Bitcoin servers. They wrote custom attacker client. using the module that is available online, written in Google language. And they use the standard Bitcoin Core clients. And from such experiment, from any experiment they run, they came up with the numbers that I just talked about. So propagation of ADDR message each 10 minutes is enough. Count for only first 10 nodes to forward transaction. And 3 entry nodes for identification is seen from the pure math. It is not important to run experiments. As a result, they managed to de-anonymize 60% of all transactions. Okay, and using statistics from such experiment, they actually calculated that successful de-anonymization in a real Bitcoin network would be 11%. In other words, you should wait for a client to send, on average, 9 transactions to be able to de-anonymize him. How this can help me in my work? So, direct de-anonymization, which is highly unlikely because that user is probably using Tor. And of course, I can exclude Tor, but then is the question if he's going to transact at all. Indirect de-anonymization. So basically, if somebody paid, if I manage to de-anonymize somebody who paid money to the person that I'm looking for, or vice versa. And again, I need to have the assistance of law enforcement agencies for to come to informations about those persons just based on the IP address and timestamp. Otherwise, I can do anything. And also, in combination with transaction graph analysis, real-time analysis can be very useful. Okay, and just some final words. So, network real-time analysis requires IP address beforehand. So basically, I can't de-anonymize anything if I don't have the IP address already available. So only thing basically what I have is Bitcoin address of the criminal. Even if I know in which network he is situated, I would need to advertise all IP range of that network just to be able to de-anonymize him. Estimated success rate of 11% for de-anonymization is very poor, and I mean, it's very hard to expect somebody to send nine transactions during one session. And the third thing is that I'm not really comfortable with doing so much connections on servers. Doing 35 connections to each server in Bitcoin network means degrading its quality of service, and I'm not really the person who would do such thing. And as I said, success rate is very poor, however. But I needed to do this research in order just to know where am I standing with this and what are my chances to do it. And I thought it is very interesting theme to talk about. But I think that I will stay on transaction graph analysis for the purpose of de-anonymization, and for sure I will not use this network approach. So basically that is all. Thank you.
Thank you very much, Marko, Maric. Thank you.